Okay, so with the analysis of the two types or three types of thermal sensors, we have concluded the part of the program that is related to solid-state sensors. And we now pass to the last part of the course that deals with quantum computation. For this, it is necessary that we go through an introduction to quantum mechanics. Of course, we shall consider only the essential parts of it that are necessary to deal with the topics of the last part of the course. It is convenient to start with the historical picture, just to show what scientists knew about the structure of atoms in the late 1800s or at the beginning of 1900. They were able to measure, for instance, the ratio of the charge to mass ratio of the electron. That quantity was measured in 1897. And a few years later, they were able to measure independently the charge of the electron. That was done in 1909. And of course, by combining these two information, they were able to also deduce the mass of the electrons. The funny part of the story is that by the end of 1800, essentially all sections of physics were well developed. Mechanics was developed first, then the electromagnetic theory was developed in the mid part of 1800, and shortly after also thermodynamics was set up in a systematic form. So by the end of 1800, the general idea among scientists was that all the important things had already been discovered. All the laws of nature at that point were known, okay? And all the remaining work by the scientists should be the applications, the refinements, and the implementation of better measurement systems to better measure all the different properties. And this is the funny part of the story, because by improving the measurement abilities, at some point they started discovering phenomena that were not well described by the existing laws. And as you know very well, by investigating phenomena at high velocities like the speed of light, they had to introduce special relativity. And by measuring phenomena that occur with very small particles, like the elementary particles, they had to introduce quantum mechanics. initial idea about the structure of the solid state metal was that of a uniform jelly of positive charge in which electrons move, okay? But that didn't work. And other experiments, essentially the experiments by Rutherford that were carried out between 1909 and 1913, showed that actual matter is essentially empty. So it is describable by what is called the nuclear theory of the atom, or the planetary theory of the atom, in which the atoms are made of small nuclei around which one or more electrons rotate. Okay? And this nuclear theory of the atom works well. It is able to explain many experimental facts without the need of introducing any new concept. Okay? But it does not explain all facts. It explains some. Okay? So the simplest possible atom is the atom of hydrogen, and in order to describe the atom of hydrogen, they simply started with the so-called planetary model, okay, in which there is one proton and one electron. So if you look at the lower left part of the figure, this is the simplest possible description of a planetary system, in which it is assumed for simplicity that the planet goes along a circular orbit. Okay, in general it is not so, but the circular orbit is the simplest one. Okay, so we have a star and a planet or a satellite that goes around with a fixed radius that is indicated with RA in this figure. Okay, and then one can apply the standard principles of mechanics for the description of this structure. We make the assumption that the nucleus is much more massive than the electron. This can be proved by independent experiments, of course, so that essentially we can consider that the nucleus is fixed in the center of mass of the planetary system. So it is sufficient only to consider the rotation of the electron around the nucleus. Then we consider that the force between the nucleus and the electron is of the Coulombic type, which is of the same type as the gravitational force. So the force is proportional to the square of the inverse radius, okay? And this force can be derived from a potential energy that is proportional to the inverse of the radius, okay? And this is important because the system is conservative. When we have a potential energy such that the force is derivable as the gradient of the potential energy, we have a conservative system. So we know a priori that the sum of the kinetic and potential energy is a total energy that is conserved in time. Okay? So there are a few equations that are in the previous page, but we must first rotate the page. Okay, so it was rotated in the wrong direction. Do it again. Okay. So if you choose the zero of the energy such that the potential energy is zero at infinity, you have the standard form of the potential energy of the Coulombic type. It depends only on the modulus of the distance between the electron and the nucleus. So R here is equivalent to RA of the other page. And the potential energy is minus Q squared times 4 pi epsilon 0, that is the permittivity of vacuum R, okay? And the force is, of course, minus the gradient of V. It turns out to be minus Q squared over Q pi epsilon 0 R squared times a unit vector, that is the vector R connecting the nucleus with the electron divided by the modulus R. The total energy, if we indicate with T the kinetic energy, the total energy, of course, is T plus V. The kinetic energy is 1/2 mu squared, in which U is the modulus of the velocity of the electron. The total energy is E and is a constant of motion, does not depend on time, okay? Can we extend this description to atoms that are more complicated than the hydrogen atom? Yes. Consider an atom in which the nucleus has a total positive charge of equal to Z times Q, and the atom has Z electrons around it. So the atomic number, instead of being 1 like in hydrogen, it is some number Z, okay? So there will be one electron that will be more external than all the other electrons, okay? So what does the most external electron see? It will see a core made of Z protons of the nucleus and Z minus 1 electrons that are internal to it, to the most external electron, okay? So qualitatively, the most external electron will see a big charge that is globally equivalent to 1 positive charge, because it is Z protons and Z minus 1 electrons, okay? So qualitatively, we can still treat at least the most external electron of a complicated atom as if it was a hydrogen Okay, of course it is more complicated. There are perturbations, but we are not considering them now. So in this more complicated case is also called hydrogenic-like system. Okay. By the way, the property of the total energy to be conserved is not limited to the case in which the electron rotates around the nucleus. Okay, actually, if we go back to the other page, there are two possibilities. One possibility is the one that we just examined, okay? So if we combine the expressions of the potential energy and of the total energy in a single diagram, if you look at the left-hand side of the figure, okay, and we report the potential energy V as a function of the modulus of R. You remember that V is inversely proportional to R, so we have a hyperbola. Okay, so this is the curve representing the potential energy. Of course, when R goes to infinity, V goes to 0. Okay? Then we may have two possibilities. One possibility is that the total energy is negative. And the other that is illustrated on the right is that the total energy is positive. Okay? When we have the case of a negative total energy, you see that the total energy, that is a constant, does not depend on position, on the radius, intersects the potential energy. What does it mean? It means that at this point, that is corresponding to this distance of the electron with respect to the nucleus, the total energy is equal to the potential energy, so that the kinetic energy is 0. If we go to the right, in this case, we have that the total energy is smaller than the potential energy, so that the kinetic energy would be negative. Okay? But a negative kinetic energy is impossible because the kinetic energy is positive definite, is 1/2 mu squared, so it cannot be smaller than 0. So this means that when E is negative, all the values of the distance are such that R is larger than the point of intersection are forbidden. In conclusion, when E is negative, the electron can stay at the distance with respect to the nucleus that cannot be larger than a fixed value. So it is always at each instant at a distance that is finite with respect to the nucleus. So this, in the very special case of a circular motion, it corresponds to this figure, but the orbit could also be different from circular, okay? In any case, the motion will be bound to the nucleus, okay? The electron cannot escape to a distance arbitrarily large from the nucleus, okay? So if, for instance, the distance is some constant RA that is indicated here, then the potential energy will be VA, corresponding to this point, and the distance from the potential energy to the total energy is, of course, the kinetic energy, that is the length of the segment or the arrow that is here on the left. Okay. The other case is also possible if it happens then that the total energy is positive, because you can see that since the potential energy approaches zero to infinity and the total energy is strictly positive, there will be no intersection whatsoever between E and V. That means that the kinetic energy will always be positive, and that the potential energy, if R becomes very large, will go to zero. Okay? And the force that is proportional to the inverse of the square of R will also go to zero. So in this case, we have that the particle can move to a distance that is arbitrarily large with respect to the nucleus. So in a description of planetary motions, this is describable, for instance, like that of a comet that comes from infinity in the space, comes near the sun, is deflected by the sun, and then goes again to infinity. Okay? So if we have a motion that is conservative, it means that if we start with the situation like the one that is depicted on the left, that is that of the bound electron, the electron will be forever bound to the nucleus. Okay? On the other hand, it may happen that at some point an external perturbation interacts with the electron and changes the energy of the electron. Okay? So in this case, there are two possible cases. Okay? That the interaction is such that the total energy of the electron changes with because of the interaction, but stays negative. So it may become smaller than the original one or larger, but still negative. Okay? Or the other case is that if we start with the negative energy and that the perturbation is large, then the electron will become free to move to infinity. Okay, so this second case is described, as you know very well, as the ionization of the atom. Okay, the electron will be torn apart from the atom and will go away, and the atom will stay positively ionized. Okay. In the other case, you remember we consider the possibility that the change in the energy of the electron does not bring to any ionization of the atom, simply the energy changes. So if the energy is changed in such a way that it goes up, still remaining negative, you see that the possible radius of the electron will increase. The maximum possible radius will increase. Whereas if the energy is decreased, also the maximum possible radius will decrease. This can be also seen by an easy calculation. So this part simply describes the two possibilities. E negative means bound electron, maximum distance is finite. E positive or even zero means that the electron may become free and go to infinity. So there is no limit to the distance of the electron from the nucleus. Okay. Then, if we consider the circular motion is the easy one. Okay, it is. Sorry. Okay, we're back here. No. Where is it? Here. No. As usual, I'm not able to. Okay, there it is. Okay, if you consider a circular motion, we can adopt some formulas that apply to the circular motion that are very instructive. In a circular motion, you remember the centripetal acceleration is equal to the square of the velocity divided by the radius. Okay, so the ratio u squared over r is the centripetal acceleration. If you multiply it by the mass, you obtain the modulus of the force. Okay. Now you remember that in general, the kinetic part of the energy is 1/2 mu squared. So you can see that there is one block in the expression of the modulus of the force that is proportional to the kinetic energy. So mu squared over r can be written as 2t over r, in which t is the kinetic energy. So in a circular motion, the force is equal to 2 times the kinetic energy divided by the radius. Okay. On the other hand, the force is q squared divided by 4 pi epsilon 0 r squared, which is also equal to minus the potential energy divided by r. So at this point, if you combine these two relations, you find that in a circular motion, the kinetic energy is equal to minus v divided by 2. And as a consequence, the total energy, T plus V, turns out to be equal to V divided by 2. And finally, we replace the expression of V so that we find minus Q squared 8 pi epsilon 0 r. Why is this expression useful? Because it shows that in a circular motion, we have a direct functional dependence of the total energy with respect to the radius. So this is an easy formula that applies to the circular motion. Okay. and tells you that since the total energy is a constant, the radius, as expected, is also a constant. Now, assume that for some reason there is a perturbation, a small perturbation in the motion, such as the motion stays circular, okay, but the energy of it changes, okay? So if you calculate the derivative of the energy, of the total energy with respect to the radius, you find that it is equal to the modulus of the total energy divided by the radius. So it is positive, okay? Since the derivative is positive, that means that when you increase the radius, the energy increases, okay? So how come that this energy may increase? Well, assume an artificial satellite that orbits around the Earth, okay? And then you apply a rocket for a few seconds, okay? So you slow down or accelerate the satellite. And then after you switch the rocket off, the satellite will find itself in another orbit, okay? Now, can we explain by this simple model not only some properties of individual atoms, but can we explain properties of crystals, for instance? You remember, we can explain properties of the individual atoms, for instance, ionization, okay? Or the inverse. If there is an ion and then there is an electron roaming around in space and they come closer, then the ion may capture the electron and constitute again a neutral atom, okay? So this is the inverse process of ionization. The other phenomenon in which the total energy is initially negative and then it increases but remains negative, so there is no ionization. In this case, since the total energy increases, we have the process that is called excitation. The external electron of the atom receives energy from outside and goes to a larger orbit that is also called excited state, okay? Or the inverse phenomenon is that the electron is excited to some higher energy state and then it goes back to the original lower energy state. And of course, in doing that, the electron must release the extra energy. Okay, so this is the process that is the opposite or the inverse of excitation. Okay. Now let's consider a crystal. A crystal may be understood as a collection of atoms, and let's assume that all these atoms are described by this model. Okay. Qualitatively, we can say that if all electrons are bound, so no electron can move freely around the crystal, of course the crystal is an insulator. We already know this. Okay. And whereas if some electrons are free to move inside the crystal is a conductor or a semiconductor. We also know this. Okay. And then we also can justify the existence of a minimum extraction energy that we call the barrier at the boundaries, okay, using this same model. So this is a very naive picture of a crystal, but just to remember some concepts. On top you see the linear monatomic chain of atoms. Okay. Then if each of these atoms was alone, then it will be the origin of a potential energy that is of the hyperbolic type. We are in a one-dimensional view of the phenomenon. So the dashed lines are, let me take, this atom is considered alone for a second, okay? So on the right of it, we shall have this hyperbola that saturates to zero, and on the left of it, we also will have the other hyperbola on the left that saturates to zero. So if this atom was alone and the source of this potential energy, when we put many atoms aside, each of them provides its own potential energy, but the potential energy of this atom will add up to the potential energy of the next atom, and so on and so on. And since all these potential energies are negative, they will add up and form this periodic structure. Okay, so this periodic structure is formed by the superposition of the potential energy of each individual atom. Of course, it is a periodical set of barriers. Okay. On the other hand, you remember we have periodicity only if the structure is unlimited. But this structure is not unlimited. There is the atom that is the last on the right, this one, and another atom that is the last on the left. So this atom will provide a barrier that is asymmetric, because the portion of the barrier on the left will sum up with the atom, with that of the atom on the left, whereas the portion of the barrier on the right will not sum up to anything because there is no other atom on the right of this. And the same happens on the left side of the structure. Okay, so this is the barrier, and this on the left is also the barrier. Okay, then if we zoom back, we shall not be able to see anymore the tiny details of this barrier. Okay, so we can take the envelope of the maxima of this barrier, and this is indicated as E alpha. You see E alpha here and there, and this level E alpha is such that all electrons whose energy is below E sub alpha, like E1, they are bound electrons. They cannot move in the crystal. Okay, if one electron with energy is 1 is in this well of potential energy, it can only oscillate to and fro forever here. So this is a bound electron. If you consider another electron that is at higher energy, like E2, this electron will be free to move inside the crystal, but will not get out of the crystal because of the barriers. Okay, of course we consider the crystal in vacuum. Okay, so there is vacuum outside. So if we zoom back, this hyperbola will become a discontinuity. Okay, and this is the barrier whose top is the asymptotic value of the potential energy of the hyperbola, and it is the vacuum level. Okay. And finally, if we provide energy from an external source to the crystal, and this energy is such that it will be able to extract one electron and bring the electron to an even higher energy, E sub 3, then this electron will be able to go away from the crystal and move to infinity, so to speak, and the crystal will remain positively ionized. Okay, so you know much of this. You know that there are 3 electrons in a crystal, or bound electrons, and that barriers on the sides. Okay, but this picture shows that simply a simple replica of the planetary model of the atoms, that is very simple, is able to justify a number of properties, not only of the single atom, but also of the crystal. Okay, we shall see next that actually there are other properties that are detected by experiments, and these properties cannot be explained with this simple model. So the model that is completely based, of course, on classical mechanics, this model must be improved. Let me check the time. Oh, we still have a few minutes. As I anticipated, there are, at the end of 1800, everybody was happy with physics because analytical mechanics, electromagnetism, and statistical mechanics were all set. Okay, but thanks to the improvement in the ability of setting up experiments were more and more refined at that time. They started finding phenomena that were not explained by the known physical laws. They are just listed here. One is the stability of the atom. Number 2 is the spectral lines of excited atoms, some aspect of the photoelectric effect, the spectrum of the black body radiation, the Compton effect, the Hall effect, and diffraction of electrons. Okay, so we shall quickly go through these aspects, because each of them is able to improve our ability to refine the model and slowly, or not so slowly, transit from the classical to the quantum mechanics. But the stability of the atom is very easily explained. Assume that the atom is really described by the planetary model. The planetary model, in the simplest form, is that of one electron orbiting with a circular orbit around the nucleus. And you remember there is a centripetal acceleration. Okay, so the electron along the orbit is accelerated because, of course, it is attracted by the nucleus. Okay, if you take the equations of the electromagnetism, you can prove that a charged particle subjected to acceleration necessarily radiates. It emits radiation. So by emitting radiation, it will lose energy. But if the electron loses energy, of course, it is like, you remember, the radius should decrease. So actually, the electron will not be able to continue on the circular orbit. It will rather spiral, getting closer and closer to the nucleus, and eventually the electron will crash into the nucleus. Okay? So the stability of the atom in the planetary model is contradicted by the electromagnetic theory. So there is one possible way out is that, yes, okay, the electron radiates, but radiates very little. Okay, so if the electron radiates very little, so that it will eventually crash into the nucleus, but in order to do so, it will take a time that is 100 times longer than the age of the universe, okay? So the phenomenon would be so slow that it would be impossible for us to detect it, okay? So actually the planetary model would do, okay, with a very good approximation. Unfortunately, it is not so, because we can calculate the decay of the electron into the nucleus using the electromagnetic theory. And the electromagnetic theory tells us that it would take a few nanoseconds for the electron to crash into the nucleus. So this easy way out does not work. So the other two possibilities are that either the electromagnetic theory is wrong or that mechanics is wrong. That is that the planetary motion is not applicable to atoms. It works for planets, but not for atoms. Okay, and this is actually the case. So the electromagnetic theory is correct, and the prediction of a radiating electron is correct. The planetary model, works well for the description of some phenomena, but it does not work well for all of them. So it must be replaced by some other model. Okay, I think that we are almost at the end of the time. We are still 2 minutes left, so we stop here, and we shall continue tomorrow on the same line by discussing other contradictory aspects or unexplained aspects of the planetary model and the solution that one after the other have been found to fix them. So we stop here for the moment.